Brake emissions have emerged as one of the most concerning sources of non-exhaust pollution from modern transportation systems, as awareness of tailpipe emissions has increased and strict regulations have forced vehicle manufacturers to improve fuel efficiency and reduce exhaust pollutants. The relative contribution of non-exhaust emissions, including brake wear, tire wear, and road surface abrasion, has grown significantly. Among these, brake emissions stand out because they consist of ultra-fine particulates, metallic fragments, and a complex mixture of chemical compounds that are easily inhaled and capable of penetrating deep into the human respiratory system. As global traffic volume continues to rise and urban areas become increasingly congested, understanding the nature of brake emissions, their harmful effects on human health, and the ways in which they can be reduced is essential for building cleaner and healthier cities. Brake emissions are generated primarily through mechanical friction between the brake pad and the rotor or drum when a vehicle slows down. Each time a driver applies the brakes, high levels of heat and mechanical stress cause microscopic particles to shear off from both the pad and the disc surface. These particles are then released into the surrounding air as brake dust. Brake systems commonly use materials such as copper, iron, steel, antimony compounds, graphite, ceramics, and various organic binders. As friction occurs, some of these materials oxidize or vaporize and later condense as fine or ultrafine particles. The most concerning fraction of brake emissions is the particulate matter known as PM10, PM2.5, and especially ultrafine particles below 100 nanometers, which are invisible to the naked eye and easily dispersed into the air around roadways. Numerous studies have shown that brake wear contributes between 15% and 55% of non-exhaust traffic-related particulate matter in urban areas, depending on the driving patterns, road conditions, and brake system design. In cities with frequent stop-and-go driving and high-density vehicle movement, brake wear is often the dominant source of metal-rich PM pollution. The composition of brake emissions is complex, and this complexity contributes to their potential hazards. Metals such as copper, iron, and zinc are often present in high concentrations because they are integral to the friction-lining materials and rotor compositions. Copper particles, for example, are released as a result of its role in enhancing heat dissipation and friction stability in many traditional brake pad formulations. Iron particles originate from rotor wear, as most vehicle rotors are made from cast iron. These metals can exist in oxidized forms, leading to compounds such as iron oxides or copper oxides, which contribute to the reactive nature of the particles. Additionally, antimony trioxide, used as a flame retardant and friction stabilizer, is another toxic substance frequently detected in brake emissions. Organic compounds from resin binders and polymers in brake pad mixtures can also degrade thermally and form polycyclic aromatic hydrocarbons, PAHs, and other volatile or semi-volatile organic substances. Friction-modified additives such as graphite and ceramic fibers further contribute to particle diversity. As brakes heat up during use, some components vaporize and later condense into nanometer-sized particles, making the emissions even more respirable and dangerous. The health impacts of brake emissions are a growing public health concern, particularly because these particles tend to be emitted near ground level, where humans breathe. Unlike tailpipe emissions, which are often discharged through elevated exhaust systems and may disperse more rapidly under certain conditions, brake emissions enter the breathing zone directly. The ultrafine metallic particles can penetrate deeply into the alveolar regions of the lungs and even translocate into the bloodstream. This penetration ability allows brake-emitted metals such as copper, iron, and zinc to reach sensitive organs and induce systemic inflammation. The inhalation of iron-rich particles is associated with oxidative stress due to their catalytic behavior in producing reactive oxygen species, which damage cells at the molecular level. Repeated exposure to such oxidative stress can increase the risk of chronic respiratory diseases, including asthma, chronic obstructive pulmonary disease, COPD, and other inflammatory lung conditions. One of the most troubling aspects of brake-related particulate matter is its ability to affect cardiovascular health. Metallic particulates have been shown to contribute to endothelial dysfunction, arterial stiffness, and systemic inflammation, factors linked to hypertension, heart disease, and stroke. Ultrafine brake particles may also interfere with the autonomic nervous system, which regulates heart rhythm. Epidemiological studies suggest that communities living near high-traffic corridors experience higher rates of cardiovascular events. And while tailpipe emissions have long been blamed, non-exhaust particles such as brake wear are increasingly recognized as key contributors. Brake particles containing antimony compounds and PAH also carry carcinogenic risks when inhaled over long periods. Children, the elderly, and individuals with pre-existing respiratory problems are particularly vulnerable to these impacts. The environmental effects of brake emissions are equally significant. Once released into the atmosphere, metallic particles settle onto soil, water bodies, vegetation, and infrastructure. Over time, the accumulation of copper, zinc, antimony, and iron in the environment can disrupt ecosystems and contaminate waterways. For example, copper is highly toxic to aquatic organisms and can impair the sensory systems of fish even at low concentrations, affecting their ability to navigate and avoid predators. Brake-related metal contaminants can also alter soil chemistry and reduce soil microbial health, compromising the natural balance required for nutrient cycling and plant growth. In urban environments, brake dust contributes to the discoloration and degradation of buildings and public infrastructure. When rain falls, water runoff can carry brake-emitted particulates into storm drains and eventually into rivers and lakes, where the metals settle and persist for long periods. This persistence means that brake-related pollution accumulates gradually, intensifying its impact despite often going unnoticed. Given these risks, reducing brake emissions has become an important objective for environmental engineers, vehicle manufacturers, city planners, and policymakers. One of the most effective methods to reduce brake wear is through regenerative braking systems, which have become standard in hybrid and electric vehicles. Regenerative braking recovers kinetic energy during deceleration and converts it into electrical energy, thereby reducing reliance on mechanical friction brakes. When regenerative braking is active, mechanical brake pads are used far less frequently, leading to substantial reductions in brake particle emissions. Electric vehicles equipped with strong regenerative braking can achieve reductions in brake wear emissions of up to 90% under certain driving conditions. This advantage not only improves air quality but also reduces maintenance requirements for brake components. Another promising approach involves the development of low-emission brake pad materials. Traditional brake pads often contain copper, which contributes significantly to particle toxicity. Many jurisdictions, especially in the United States, have phased out or restricted copper-based brake pads through environmental legislation. The move toward copper-free brake pads has led to the development of alternatives such as ceramic brake pads, which produce fewer particles and generate less heat. Ceramic-based pads also tend to produce lighter, less toxic dust composed primarily of non-metallic materials. Similarly, organic brake pads made from fibers like Kevlar, carbon, or resin composites generate fewer heavy metal particles. Advances in friction material science continue to explore additives that enhance durability and reduce particle formation without compromising braking, performance, and safety. Vehicle manufacturers are also developing brake disc technologies designed to reduce particulate release. One of the most notable advancements is the use of coated brake discs. These discs feature surfaces treated with tungsten carbide coatings or other hard-wearing materials that significantly reduce rotor wear. Because a substantial portion of brake particulate matter comes from rotor abrasion rather than just the pads, coated discs can dramatically decrease the emission of iron-based particles. In addition to reduced emissions, these discs also enhance brake longevity and performance. Some companies have created brake systems specifically designed for electric vehicles, optimizing them to work in combination with regenerative braking and reduce friction-based braking even further. Another innovative solution gaining attention is the use of brake dust collection systems. These systems employ small devices mounted near the brake assembly that use airflow suction, electrostatic attraction, or mechanical traps to capture brake particles before they are dispersed into the air. While still relatively new, early prototypes have demonstrated the ability to collect a significant portion of brake wear particles. If widely adopted, such technology could greatly reduce urban exposure to brake dust, especially in congested areas with frequent braking cycles. Urban planning strategies also play a critical role in reducing brake emissions on a population-wide scale. Traffic management solutions, such as synchronized traffic lights, roundabouts, adaptive speed limits, and improved public transportation infrastructure, help maintain smooth traffic flow and reduce the frequency of abrupt braking. Smoother driving conditions not only cut down on brake emissions but also lower fuel consumption and decrease overall transportation-related pollution, encouraging alternative mobility systems like cycling infrastructure, pedestrian-friendly urban layouts. And electric public transit reduces vehicle numbers and the associated brake wear. Low-emission zones that limit access to older, heavier, or non-regenerative vehicles can further reduce brake particle pollution in densely populated urban centers. Driver behavior also influences brake emissions. Aggressive driving, characterized by rapid acceleration followed by sudden braking, significantly increases brake wear. In contrast, defensive and anticipatory driving practices reduce the need for friction braking. Many modern vehicles come equipped with driver assistance systems that encourage smoother driving, such as adaptive cruise control, collision warning systems, and automated braking. As these technologies become more widespread, they will help reduce brake wear and improve road safety simultaneously. Despite the promising toolbox of solutions, reducing brake emissions poses challenges. One of the most significant limitations is that even with improved materials and regenerative systems, mechanical braking cannot be eliminated entirely. Safety requirements mandate that brakes perform reliably in all conditions, including emergencies, high speeds, and low battery scenarios in electric vehicles. Therefore, some level of brake wear will always be present. Additionally, the widespread adoption of regenerative braking depends on the uptake of hybrid and electric vehicles, which varies significantly across regions due to differences in economic conditions, charging infrastructure availability, and consumer priorities. While electric vehicle adoption is accelerating in many countries, large segments of the world still rely heavily on conventional gasoline and diesel vehicles that will continue to generate brake emissions for years to come. Another challenge lies in the cost of advanced brake materials and technologies. While ceramic brake pads and coated rotors offer clear environmental and performance benefits, they tend to be more expensive than their traditional counterparts. Fleet operators, lower-income drivers, and developing countries may face barriers in adopting these technologies. Although costs are expected to decrease as production scales up, the transition will not be uniform across all regions. Brake dust capture devices, while promising, are still in the early stages of development and are not yet widely commercialized. Their long-term reliability, cost-effectiveness, and maintenance requirements remain areas of ongoing research and testing. Furthermore, non-exhaust emissions, including brake dust, are not regulated as strictly as tailpipe emissions in many jurisdictions. While some regions have enacted laws targeting specific materials like copper, there is still no comprehensive global regulatory framework addressing brake emissions. Without regulatory pressure, manufacturers may lack incentives to innovate rapidly or transition fully to cleaner alternatives. Policymakers must take into account the scientific evidence regarding brake emissions' health impacts and incorporate non-exhaust pollution into air quality standards and transportation policies. As we move toward a future with cleaner transportation, it is clear that addressing brake emissions will be a critical part of the solution. The shift toward electrification will help reduce mechanical brake use through regenerative braking, but it will not solve the issue entirely. Continued research into low-emission materials, coated discs, brake dust capture systems, and improved urban infrastructure will be essential. Additionally, education initiatives that encourage smoother driving habits can yield immediate benefits without requiring major technological changes. Ultimately, mitigating brake emissions will require a multifaceted approach involving engineers, policymakers, vehicle manufacturers, city planners, and drivers themselves.